Gilles Frache, from Luxembourg Institute of Science and Technology. Yes. And he is specialized in MALDI method development. And so, thank you to be here and welcome.
Thank you. Good morning. Thanks for being here. I will give a talk focusing on the coupling of the AP-MALDI source with Orbitrap instruments and gives you some information about our recent developments. So just a reminder, the benefits of this AP-MALDI source from MassTech is that it can be coupled to a wide range of high-resolution LCMS instruments. So I will focus more on the Orbitraps. So it can be coupled to old generation Orbitraps like the LTQ Orbitrap, Elite or Q-Exactive series, but also on all the range of modern instruments, including the latest ones like the Astral Zoom or the Excidian. So in our lab, we have started using the AP-MALDI source a long time ago with the Orbitrap Elite, and since 2022, we have moved all the AP-MALDI activities on an Exploris 480. More recently, I had the opportunity to test the AP-MALDI source, so it's very small. You can see the source on the booth. I put my source in a small suitcase, and I traveled to the south of France to try the AP-MALDI source on an Astral during 2 days. And I will show you a few results that we obtained only in 2 days. So just a reminder, the benefit of the source is that it's really a flexible source. So typically it takes really 1 single minute to switch from an LCMS configuration to an AP-MALDI configuration. So you just remove the electrospray block.
The video is sped up. No, I'm joking.
No, real time. So we just put a small extender to reduce the distance between the entry of the mass spectrometer and the sample plate and increase the electric field. And we attach the AP-MALDI source very quickly. We close the 2 brackets. Then we connect 3 cables. The synchronization, the communication cable, the synchronization cable in the right direction, and the power cord, and we can start working. So really 1 minute. So it's very convenient because you can also switch back to electrospray, calibrate the instrument, completely calibrate the instrument, not only the mass scale, but the complete instrument. And everything is integrated in the box. So we have the solid-state laser, which can be operated between 100 Hz and 10 kHz. Everything is laser safety compliant, and we can focus the laser to 10 micrometers or less. All the optics, the electronics is included, and we have a high accuracy sample stage with an accuracy of 5 micrometers. Okay, so the typical workflow is that we can combine the usual bulk analysis using high-end LCMS instrument and take benefit of all the features of a Orbitrap instrument, so full scan, data-dependent analysis, data-independent analysis, targeted analysis, and we can also use the new Acquire X workflows to have improved method development. But we can use the same analyzer and all the same features for AP-MALDI imaging. So we can use in-pixel full scan and MSMS modes, either using the same analyzer in Exploris instrument or using parallel detection with tribrid instruments. So the workflow for imaging, as you have been, as we have seen already today. So we prepare the sample, that's the most important part. And then we will use the laser in a continuous mode, so meaning that we will produce ions continuously during each line of this area of interest. Then we have collected spectra from each pixel, and we can use different software to display the results. So there have been many improvements on the ease of use of the source with the great work of Konstantin and all the team at MassTech to make the user experience very easy and very straightforward. So there is now the new target software, which allows for the control of the source in a very easy way. So we can import an optical image of the sample and directly navigate on the optical image. There is also a way to have a preview of the stage using stitching from the video camera inside the source, but it's very convenient to import an optical image. We can zoom in directly in the software and define precisely which will be the regions of interest. So there is no need to record a rectangular image and waste time analyzing the sample holder, of course. So biology is not really rectangular, so it's very convenient to define regions of interest of any shape. Another interesting feature is that we can collect multiple images from the same section. So if the pixels are big enough, there is remaining space between the line coming from the first analysis. So we can use this space between the line to record a second analysis from the same tissue section. So we can use the first analysis for a full scan in positive ion mode, second image for negative polarity, for example, or for MSMS scans in a second acquisition. Okay, so the other benefit is that we can run sequences of imaging, which is also interesting to leave the instrument run over the weekend and not only starting one image and that's it. So we can set up a sequence of imaging. So from the mass spectrometer, from the source side, we will define regions of interest depending on the imaging parameters, so the pixel size, the size of the regions of interest, and the acquisition parameters. The software will calculate a duration that will be useful to define the method on the mass spectrometer side. So the workflow before the acquisition is to prepare the sample, which is the most important part, and the matrix deposition using the best possible sprayer is an important step. Then we define the parameters for the image acquisition on the MassTech source. Then we define the MS parameters on the thermo software. And we prepare the sequence exactly the same way as we would do for an LCMS sequence. And then we start the acquisition, and we can go on weekend, for example. Then the instrument will run automatically, and after the acquisition, we just need to recover a position file, which is a file giving the link between the scan number and the X and Y position. And we'll get a position file for each region of interest, and we'll combine this XML file with the raw file from the mass spectrometer using the MassTech converter. We will create IMZML files for each region of interest. And then there is a range of possible software solutions to handle this imaging data. So there are open source platforms like Metaspace, software like MZMind, which has some features of interest. But also there are commercial systems which are more advanced for data processing, annotations of the peaks, library search and things like that, and also statistics, segmentations, and things like that. So there is a range of possible software. This is a typical example of a mouse brain imaging experiment from a brain with a traumatic brain injury. So to investigate the effect of the traumatic brain injury on the one side of the brain. And you see that's a quite quick imaging experiment, so using only 45,000 resolving power on an Exploris 480 with a pixel size of 20 micrometer. So it took about 4 hours to cover the whole tissue section. So of course we could take more benefit of the ultra high resolution of an Exploris 480, but in this case the scan rate would drop from about 10 pixels per second down to about 1 pixel per second. So the same image would take 10 times more for the whole acquisition. So of course it's always a balance between the number of pixels, the pixel size, and the mass resolving power. So it's always a trade-off. Okay. So anyway, the source can accommodate with any of these possibilities. Okay. Right, so that's an example of a single pixel in the phospholipid mass range. So that's a typical typical spectrum. Okay. So just a few words about the 2 days of tests that I could do on an Exploris, on an Astral, sorry. So it was in Toulouse in the south of France. So typically we always start each installation with a spectrum from a peptide mixture. So it's a mixture of 5 different peptides. So I wanted to compare the spectra collected in the Exploris part of the Astral. So there is an Exploris 480 coupled to the Astral. So if we want to take an average mass spectrum of this peptide mixture at a mass resolving power setting of 120K, it takes about 200 milliseconds for the scan acquisition. If we want to take maximum benefit of the high resolution, it takes about 1 second. If we want to have a kind of full scan in the Astral, just to compare the sensitivity, so we just set up MS2 without collision energy and with a very broad ion selection. So it's what we call a pseudo full scan experiment. So to get a high resolution mass spectrum in the astral, which have about 70,000 resolution all over the mass range, it takes less than 35 milliseconds in this case. It could be even faster. So it opens new perspectives for AP-MALDI imaging when we use the astral instruments. So of course, looking at the isotopic patterns, we have the full detection of all the isotopes from a peptide. So yeah, good sensitivity, but much higher scan rate using the astral. So of course, we can use the astral with only the Exploris detection, so only the Orbitrap analysis. So we finally get the same result as what I used to get with my Exploris 480. So this is an example from the team in Toulouse. So again, a lot of detected features in the lipid and phospholipid mass range, and a lot of annotations automatically given by Metaspace, again, based on the full scan. Okay, so as I said before, we collect the raw file, we collect the position file, and we can create an IMZML that we can upload in Metaspace and get annotations based on the full scan. Just an example, I wanted to compare the relative sensitivities between a very short full scan in the Exploris and a pseudo full scan in the Astral. So yeah, the spectrum on the top is a very short injection time of 5 milliseconds in the Exploris. We could detect about 50 features directly from the tissue in a single pixel. And if we compare with the spectrum at the back, at the bottom, sorry, it's a pseudo full scan in the Astral with an injection time of only 16 milliseconds. Okay? And we see more than about 8,600 features in the spectrum, which shows a dramatic improvement of sensitivity using the Astral as a full scan analyzer. So it gives some ideas for the future using the Astral for imaging. But of course, the typical use of the Astral would be to use the full scan in the Orbitrap and MSMS in the Astral. So just an example of what we could do to increase the scan rate using the Astral, the Orbitrap only. So we can scan up to 15 pixels per second. So that's just a small part of a biological tissue. The image was collected in only 6 minutes using the Astral in pseudo full scan mode, which gives a 75,000 resolving power. So if we would use the Exploris at the same scan rate, 15 spectra per second, 15 pixels per second, we would have only a mass resolving power of 7,500. So it means that using the Astral in the pseudo full scan mode gives a 10 times improvement of the mass resolving power for the same scan rate. Otherwise, we could consider that if we would want to work with about 75,000 mass resolution in the phospholipid mass range, we would need to use the setting of 120,000. So it means that in this case, the scan rate would be only 3.7 scans per second. So yeah, clear benefit. So going back to the question about the identification in MALDI imaging, yes, of course, we can use the Astral to improve significantly the quality of the identification. So in normal conditions, people would use the Orbitrap for the full scan analysis and take the maximum of benefit of the Astral for MSMS scans. So we set up a short experiment on a skin section, which was only a 40-minute acquisition at 10 micrometers per pixel, using a setting of resolution in the Orbitrap at 240K. That's typically what we do in most of the cases. And we used the Astral for 4 targeted MSMS scans, so to have always for each pixel the same MSMS transition, and we used the remaining time for as many DDAs as possible. So in this case, we could increase the number of scans, so that's only in 2 days, so I'm pretty sure we can improve this, but the experiment contained for each pixel, so about 800 milliseconds per pixel, we had one full scan at a very high mass resolution power, 4 targeted images, and 12 DDA scans for each pixel. So of course, we can extract the full scan images of selected molecules. And also we could select randomly from DDA scans, MSMS spectra to confirm the structure of, for example, these lipids and confirm the class and also the structure of the chain lengths and carbon positions, double bond positions sometimes for lipids directly from the DDA scans. So only after 2 days of experiments on the Astral, yeah, we have seen a clear benefit and clear perspectives for AP-MALDI imaging on the Astral. We still keep the possibilities with the Exploris to have very high mass resolution, very high mass accuracy, and a very good stability over time. So that's what we have already seen for the Exploris 480. But the coupling with the Astral, being the standard Astral or also the Zoom or the Excidion, so it opens more perspective in terms of dynamic range, in terms of scan rates, and the number of MSMS scans that we can get. So in terms of identification, it opens new perspective to ensure what molecules we are mapping in MALDI imaging. So of course, it was a challenge to deal with all this data because over 40 minutes we collected 17,000 DDA scans. So the amount of data that we need to treat after such a quite short experiment was a challenge, and we worked a lot with Constantine to also improve the data treatment and to have a way to convert all these scans to extract a maximum of information from this complex experiment. So yeah, we see now that the Astral needs a lot of ions because it's able to work a lot with all the ions. So it means that in the past, with the old instruments, we could take our time to produce ions because the Orbitrap Elite was quite slow and not so sensitive. With the Exploris, we have seen that now, yeah, we need to fill the Orbitrap quite fast compared to what we used to do with the Elite. Now with the Astral, we see that, yeah, we need to keep the second analyzer busy. So it means that we need to produce more ions. So this brings me back to some of our developments on the ionization front. And I want to mention here one of the prototypes that we have developed with MassTech through a partnership that we have started a couple of years ago, where we wanted to evaluate how we can increase the ionization yield using laser pulse ionization at atmospheric pressure. Because we have seen, and I have done this many years ago when I was a PhD student, laser pulse ionization can increase the sensitivity by 1 or 2 orders of magnitude in MALDI analysis. So of course, that's what we expect for imaging. But the question was, is it possible to do that at atmospheric pressure? Yes, after a lot of work, we managed to develop this proof of concept, which is an add-on which can be attached below the AP-MALDI source. So there is just a hole drilled at the bottom of the AP-MALDI source, plus a little bit of photodiode for the timing. And the second module, the one at the bottom, contains the post-ionization laser, which is a 266 nanometer laser, which is synchronized with the first laser in the AP-MALDI source to induce laser post-ionization at atmospheric pressure. So, just a comment, the whole system can be removed and we can still switch back to electrospray within 1 minute. So the whole system is a bit heavier, but it still remains very flexible. So what is the benefit? So we analyzed a standard of lipids, and we see between the AP-MALDI and the AP-MALDI 2 a significant improvement of detection, an improvement by 1 or 2 orders of magnitude. So it works, yes. Yeah, we can do AP-MALDI 2. It works. Post-ionization at atmospheric pressure increase the sensitivity. So of course that's for mass spectrum. But of course what we want to do is imaging. So you can see on these images, on the right side, that's the conventional AP-MALDI image. So there are some lipids which ionize well, like the PEs or the PC. So in this case, we see an improvement of detection with the laser post-ionization. But interestingly, for the other lipids that are shown here, they are not or barely detected with the standard AP-MALDI source, but with the post-ionization, we can make them visible. So that's really the benefit of laser post-ionization. It can reveal new molecules which do not ionize well. And we have also a slightly different ionization mechanism. So this is something we like to discuss with Eugene. What is the benefit of having different wavelengths in terms of ionization mechanisms? And we can really reveal different molecules because we can have a kind of second MALDI event, but also we can have a kind of photoionization, so leading to radical cations for specific molecules, including drugs, which can open interesting perspective also for this prototype. All right, so this brings me to my conclusion. So I think you have seen that the AP-MALDI source is a very flexible ion source for Orbitraps. It allows us to switch very quickly from different Orbitraps also. So if you have different Orbitrap or different thermal instruments in your lab, you can start with a high-end Astral for discovery approach with the ASMS, and then once you have a selected list of molecules, you can switch to a different instrument, for example, a Stellar, to do only a targeted approach using the same AP-MALDI source. It is already compatible with the Astral Zoom and the Excidion Pro because it's like the other thermal instrument, you just attach it and you can start working. And as you have seen, the Astral opens a lot of new perspectives in terms of MSMS analysis. And yeah, the laser pulse ionization works also at atmospheric pressure, so that's something we have been demonstrating with MassTech through this collaboration over the last years. Right, so thank you for your attention.
Thank you for the presentation. I hate to be the police time, but with that, I think we close our breakfast seminar. Please feel free to reach out our speakers for any other questions. And thank you all of you for attending this breakfast seminar. And so enjoy the rest of the conference.